Okay. So welcome guys. So in this video, so previously we already discussed what is the main transform. So this is the lecture to a main transform. Okay. So in the lecture two, we first proved these common properties, and that we proved the Perron's formula, basically the inverse main transform. Okay, so let's start. So just remind you guys that I built a subscribe channel, a subscribe button in every PowerPoint, right? So okay, so just remind you guys that you should subscribe. I hope you guys subscribe. Okay, so let's remind you guys. So m of f of t will be 0 to infinity f of t x to the s minus 1 dt. Okay, so the first one is the delta t minus n. Sorry, so this is stupid. T minus n x s minus 1 dt. So definition will be put t to b. So this is what I'm writing about dx, right? So this is t minus n, right? So what we can do is just do. So this is x. X. Okay. So we put t equals to n, right? So it's n as s minus 1. Okay. Sorry, because this is, if this is t, then everything should be t, right? Except for this is s. Also for this one, that's 0 to infinity. This is called a scaling property, right? So this is scaling property is very famous in like Fourier transform, Laplace transform. Okay, so it's like f of at, t to s minus 1 dt. Okay, so let's that maybe the at equals to y, right? So it's 0 to infinity f of y, y s minus 1, a s minus 1, and the dt, right? Dt is dy, right? So a dt is dy, right? So dt is dy divided by a. Okay, so just remind you guys that a should not be 0. Okay, so a s, okay, and 0 to infinity f of y, y s minus 1 dy. So this guy is the Mellin transformation of f of t, right? Because this is dummy variable and a variable s, so just times this factor. Okay, so common properties. Okay, so next is the important one, basically the famous one is called the Perron formula. Oh, so Perron's formula also famous in number theory. If you see if you want to derive some consequence of Riemann hypothesis, and or basically give an upper bound of some. Basically, these Perron formulas will connect the number theory to complex analysis. So this is very important. And in this video, we only prove the simple one. So no error bound. Okay. So what we want to prove is that if you have y to s divided by s, b to the what I'm writing about. So it's b minus I infinity, b plus I infinity, and so basically your integral is like this is b. Right? You go left, you go this b minus infinity to b plus infinity, and y to s ds 1 over 2 pi I. And y is a real number, okay, and y is a positive number, and we only have 3 consequences. B is greater than 0, okay, so if y is greater than 1, and b is 1, y is 1, the answer is half. Y is between 0 and 1, the answer is 0. Okay, okay, so the proof basically this formula is interesting. So proof is basically using complex analysis, and we prove three different circumstances. Okay, so the first one is that's proof. Okay, let's prove the y greater than 1. Okay, so if y greater than 1, right? So you can imagine that if y is 2, right? So let's say y is 2, then it's 2 to the s, right? So you see that if s is very negative, basically real s is very negative, then 2 to the s will be 0. Okay, so if I plot the contour, then I should use this red plus this orange, right? Because we know that we know that if I choose a real s to be less than 0 and very negative, then y to s will be 0 because y is greater than 1. Okay, so by the complex analysis, we know that the orange one plus the green one, the orange one plus the red one, which is red is what we want, equals to the residue, right? The residue of this f of s will be y to s divided by s. Okay, so the only pole is s equals 0, so it's res equals 0. So So you just put s equals to 0, right? So it's y to 0, which is 1. And you can easily prove that, right, because y is greater than 1. So if s is very negative, then you can prove that this orange is 0 just by the ordinary complex analysis. So I don't want to show in detail here, but this is trivial. Okay, so the r goes to infinity. This is 0. So we prove this is 1. Okay, so it's obvious that when y is less than 1 and greater than 0, then you just choose the green circle to be your complex contour. Okay, so the second one is the same. You just contour, but if you choose this contour, then there's no pole, right? There's no pole here, so you get 0, right? And this term will also be 0. So you prove the second case. Okay, the third case is also a little bit tricky, because when y equals to 1, right, what we need to compute is this. Okay, so maybe I choose this right, this green one, this blue one, right, and this is a circle. So you see that if let's say s equals r exponential I theta, then s whatever ds, right, will be r I exponential I theta d theta r e I theta, right? So you cancel, so it becomes I theta. Right, so you see that if I this is a famous widening number. If I run a circle, then it will be 2 pi. Right, so you see this green, this red plus this blue, right, will be 0 by the previous one. But for this for this blue one, right, if r goes very large, then you see this is just a round circle, half circle. So this will be negative pi I. Okay, why negative? Because this is the clockwise, right, and the 2 pi in positive will be counterclockwise. So this is negative pi I divided by 2 pi I. So you can prove. So it's easy to see this is a half. Okay, so this is basically a complex analysis lecture. I mean, if you don't know the complex analysis lecture, I have a playlist. I will put in here. Okay, so you can check my complex analysis lecture. Okay, so Perron's formula. Okay, so if you go to Wikipedia, right, and Wikipedia say that the Perron's formula basically is this. So now we can connect it my previous Perron's formula to prove this Wikipedia's true Perron's formula. Okay, probably nobody cares. Okay. So the A and B are arithmetic function. So arithmetic function means that A is a function from natural number to complex number. Okay, so any function which from natural number to complex numbers are called arithmetic function. So number theory basically basically number theory basically just research on this arithmetic function. Okay. So one obviously definitions define g of s to be a divided by n to the power s. Okay, so this is a very famous series, right? If you choose a n to be 1, then you get 1 over n to the s, which is a Riemann zeta function. All right, and if you do other, then you can get a Dirichlet function, and basically very, very exotic function. Okay, so this is called a Dirichlet series, right? If you put a and divide this. Okay. Now let's say this g of s is well defined by some after some sigma. After sigma is some real number. Okay, so basically we assume that g of s convergent for some good region. Then Perron's formula say that you can define a to x, right, to be n less or equal to x, a n. So this is well defined, right? This is well defined, right? Because for every x, then there's only finite term. I need to sum, right? So, and the complex number definitely can be summable, right? So it's well defined. Well equals to 1 over 2 pi I c minus I infinity plus infinity g of z, x to z dz. Okay, so this is the famous result. Okay, so Wikipedia say that prime number summation equals last term. So the strange case is that if x is even integer, then last term must multiply by half. Okay, when x is integer. So when x is integer, then you need the last term must be times half. So you see it's obviously just this guy. Okay, so we will prove it is. Okay. Okay, so this is the final PowerPoint of the Mellin transformation. So basically, once you understand Perron's formula, then most of the Mellin transformation you already understand. Okay, so what else we can do, right? In order to prove this, we just put this g of z into this, right, and then we prove from right hand side to the left hand side. Okay. So this is right hand side, right? So you can just shuffle, right? Shuffle this into just exchange with this integral and summation. So uniform conversion is very important, right? To exchange this. Right, and then you change this to this. So basically, you just combine this x and z, right? X divided by n to z, dz divided by z, a of n, c minus infinity, c plus infinity, n from 1 to infinity. Right, and then you put out all of these integral, right? You get this. X divided by n dz, dz divided by z, right? So by definition, we know that these guys, this. So in order to this one to be 0, then x divided by n must greater or equal to 1, right? So that means if x is not equal to n, then x divided by n equal to 1, then it must imply x greater than n, because n is any integer, right? If x is not integer, then this always holds. So this term becomes a of n, n less or n less or equal to x. Okay. If x equals to n, then you need to do the same thing. This term is still the same, but the final term, right? The final term must times a half due to this term, right? So if x equal to z, sorry, if x is integer, then x divided by n is 1, right? So you will have this term. Okay, so this is the true Perron's formula, and then once you have this true Perron's formula, then you can do the so-called inverse Mellin transformation. So I think the final video will be the last video of the Mellin transformation. Okay, and okay, so hope you must subscribe to my channel. Thanks.